So you've just met monogamy and you've seen how to understand it as a property or restriction of entangled states. One way to formulate monogamy of entanglement is to say that there does not exist pure tripartite states, psi on A, B, and C, such that each of the reduced states on A and B, A and C, also B and C, is a pure entangled state. So in this way, the correlations that arise from entanglement cannot be shared. You cannot have strong form of entanglement, pure bipartite entanglement between A and B, and also between A and C at the same time. What we're going to see in this module is that the monogamy of entanglements has consequences even at the level of the correlations, of the classical correlations that can be generated from the states. So let's see how this demonstrates itself on a little example based on the CHSH game. So you've seen the CHSH game as a game that's played between two players. So let's review what this game was. So let's play it between Alice and Bob. So Alice and Bob each get an input, X, which is in 0, 1, and Y, which is in 0, 1. They have to produce outputs, A in 0, 1, B in 0, 1, such that A plus B is equal to the AND of X and Y. And you saw that there's a way for them to achieve this by sharing an EPR pair, maximally entangled state of 2 qubits. So if Alice and Bob share the state psi AB, which is 1 by root 2, 0, 0 plus 1, 1, then they can achieve these correlations with probability cos squared pi over 8. Right? This was this roughly 0.85, and that beats anything that they could do classically without using any entanglement. So that's the CHSH game. Now I can imagine playing the exact same game instead of between Alice and Bob. I can also play the game between Bob and Charlie. So I would provide an input Z, chosen uniformly at random in 0, 1 to Charlie. Charlie has to produce an output C. And again, using the same strategy, if Bob and Charlie were to share a maximally entangled state, psi BC, then they would be able to produce correlations that satisfy the CHSH constraint, that the parity of B and C is equal to the AND of Y and Z with probability cos squared pi over 8. Nothing special here. But the question that I want to ask is it possible to get the best of both worlds simultaneously? This here I am assuming that Alice and Bob share this state psi AB and they play the game between them, so they're told who they're playing the game with. In particular, Bob knows that he's playing with Alice, and in that case, he knows that he should be using this qubit. Or Bob could be playing the game with Charlie, in which case he should be using this qubit. But what if Bob is not told with whom he's trying to play the game? So the question that I'm asking is, does there exist now a tripartite entangled state, psi ABC, and measurements, local measurements on this state that produce outputs A, B, and C for Alice, Bob, and Charlie, such that these outputs would reproduce the same correlations as Alice and Bob if they were just playing the CHSH game on their own, and Bob and Charlie if they were just playing the same game on their own. That is, I am trying to maximize the probability that A plus B equals X and Y, plus the probability that B and C equal Y and Z, weighted by a half, as if I was playing the one game with probability half or the other game with probability half, without telling the players which game they're playing, but still providing their inputs and looking at their outputs. So I'm evaluating these two probabilities on the same state and the same measurements, and I want to know what is the maximum probability that's achievable. So if they were able to play the CHSH games as, they can if they just know with whom they're playing it, then this should be a half of cos squared pi over 8 plus a half cos squared pi over 8. I should get cos squared pi over 8, about 0.85. Well, in fact, what you can show is that this expression for any tripartite state and any measurements is at most 3/4. And 3/4 is what you can do classically. It's easy to achieve 3/4. Alice, Bob, and Charlie all the time output 0. They don't need any entanglement if they always output 0, and I choose the inputs X, Y, and Z uniformly at random, then this expression will evaluate to 3/4. So this is extremely surprising. It's saying that there is no advantage at all to using entanglement if you try to play this 2 among 3 players variant of the CHSH game. This is going to be something that's going to be very powerful in cryptography, because it means that in a way that if Alice and Bob achieve strong CHSH correlations, so if this expression is cos squared pi over 8, let's say, because it's something that they verify by checking their correlations in between themselves, then this expression here, by virtue of the inequality I wrote down, must be at most 3/4 minus cos squared pi over 8, meaning that it can definitely not achieve the quantum bound. Actually, it must be much smaller. So how do you prove such a thing? You'll see more details in your homeworks. It's not easy, because how do you know, right? You'd have to optimize over all possible tripartite entangled states, all possible local measurements, any dimension, and see what is the best strategy. You don't really have an idea. You could use the GHZ state or maybe some other kind of state. Who knows? The idea to prove a bound is going to be to consider even more general strategies for the players that are so-called non-signaling strategies. That is, we are going to model these three boxes here using the family of distributions on the outputs A, B, and C conditioned on the inputs. And we could say that we restrict our attention to those distributions that can be generated by quantum mechanics. But in fact, we're going to look at a broader class of distributions, so-called non-signaling distributions, which allow for more correlations, but have the advantage that they're easier to work with because the constraints are easier to express. And you'll prove that this bound of at most 3/4 holds for non-signaling distributions. And because they're a broader class than quantum distributions, then you'll deduce that the same bound holds for the distributions that can be generated using entanglement. So this is another expression of monogamy. It's expressed at the level of correlations rather than at the level of the entangled state of the Schmidt coefficients that we saw in the previous module. And it's the kind of form that's going to be the most useful for cryptography. Because when you do cryptography and you're Alice or Bob, you don't know what the quantum state is that you're sharing. The only thing you know is the kind of correlations that you can generate. This is something that you can check in between yourselves. You can perform the measurements, see if the correlations are strong or not. And so secrecy in cryptography, in particular in quantum key distribution, is going to rely on verifying such strong correlations between the honest parties to serve as a guarantee that there are no further correlations with a potential eavesdrop. So we'll talk much more about this in later modules.